Hey Calculus class, today we are going to talk about topic 11, derivatives and differentiability. So we're going to first talk about the derivative as a function. Given any number x for which the limit exists, we define a new function f prime, which is what this little tick mark means, f prime of x, called the derivative of f by f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. To keep in mind, the function f prime can be graphed and studied just like any other function. So when we have a derivative, there's multiple different symbols and we say them differently. So the first one is when you have f prime of x, we say f prime of x. And this is most common, but does not name the dependent variable, which is y. Then we have y prime, said y prime. This is nice and brief, but does not name the independent variable. Then we have dy dx, or otherwise said, the derivative of y with respect to x. This names both variables and uses d for the derivative. The next one is called df dx, or the derivative of f with respect to x. This emphasizes the function's name. So this could be whatever your function is. So if it's g of x, you would say dg dx. Then there is this one, which says d dx of f at x, or the derivative of f at x. This emphasizes the idea that differentiation is an operation performed on f. Then there's these two. These ones you won't see on the AP test or in our book, but they are common in college. And basically it's just the derivative of f at x. And you can see it either way. So it's possible that the college professor might write this on the board just to prepare you. Now we have what is called a Lebanese notation. Lebanese notation, sorry. Always mispronounce this. Lebanese notation. And the dy dx notation is called Lebanese notation. This notation comes from the increment notation. That is, dy dx is equal to the limit as the change of x is approaching 0 of the change of y over the change of x. This is just the slope of your secant line as the change of x is getting closer and closer and closer to 0. If we want to indicate the value of dy dx at the value a using Lebanese notation, we write dy dx at x equals a. And this bar right here, I'm not sure if you've seen it before, but this bar just means to evaluate at x equals a. All right, so let's take an example. So let's say we want to find f prime of x, so the derivative of this function in general, not at a specific point or anything. So that means I am going to use my limit as h approaches 0 of f of x plus h minus f of x all over h. So I'm going to plug in x plus h into my function, and then I'm going to plug in just x. So when I do that, I get the following. Now I'm going to simplify a little bit. And to do this, well, technically, let me back up. If I was to plug in 0 right now, I would get 0 over 0. It tells me I've reduced some type of algebra. Since I have a root on the numerator, I am going to rationalize the numerator. So I multiply the top and bottom by the conjugate. Now, when I distribute the top, I got a difference of 2 squares. So the roots cancel on the numerator. And on the bottom, I just have h times all this stuff. Do not distribute the h through, because eventually our goal is to cancel the h. Now I can go ahead and expand out the x plus h squared, distribute this negative sign to get the following. Now I'm going to look for stuff that I can cancel. The x squareds cancel, and so do the 2's. Now I can see that my remaining terms have an h, which is what you want to happen, so you can factor out an h. Now the h's cancel, and I am left with the following. So I can go ahead and plug in 0 for wherever I see an h to get the following. Now I just simplify. So I got 2x plus 0, just leaves me with 2x. And on the bottom, I'm just going to be left with x squared plus 2 plus x squared plus 2. Of course, the square roots. Since these are the same, I can go ahead and combine them. So now I have 2x over 2 times the square root of x squared plus 2. The 2's cancel. So my final answer is x over the square root of x squared plus 2. Basically, this function is my derivative function. I can use this function to calculate the slope of the tangent line on this function at any given x value. All right, our next topic is differentiability. The definition of differentiability is a function f is differentiable at a, and when I say differentiable, that means that you can draw a tangent line on the curve at that specific x value a, if f prime of a exists. So the tangent line exists, that means you can calculate the slope of it. The function f is differentiable on an open interval, and an open interval could be anything as a to b, or a to positive infinity, or negative infinity to a, or all real numbers, so negative infinity to infinity, if it is differentiable at every number in the interval. Now we have a connection between differentiability and continuity, and this is a big theorem to remember. If f is differentiable at a, then f is continuous at a. So if you know that you can find a tangent line, therefore calculate the slope of the tangent line on the curve, then the function is considered also continuous at a. However, the converse of this theorem is false. That is, there are functions that are continuous at a point, but not differentiable at that point. And I will show you examples in just a minute. So, how can a function fail to be differentiable? A function f can fail to be differentiable in 3 ways. The most common is what is called a corner or a sharp point. The graph will look something like this. The most common example I like to use for a corner is the absolute value graph. We know that the absolute value graph is a v. So therefore there is a corner. At that corner point, it is not differentiable. And the reason why you cannot take the derivative at a corner, because if I wanted to draw a tangent line at this point, where would the tangent line be? I would have too many. So you could draw one here, you can draw one here, etc. So the idea that this is why a corner point is not differentiable, because there are too many options. The next one is the graph can have a discontinuity. So a graph can look like this. You cannot take the derivative, or in other words, find a tangent line at a discontinuity like this. And it's pretty much the same reason at the corner. You can draw more than one tangent line. And that tells you that you can't take the derivative. There can only be one tangent line at a point on a curve. And the third one is the graph can have a vertical tangent line. So something like this. And the reason why this is not differentiable is because what is the slope of a vertical line? It is undefined. So therefore, the derivative would be undefined at a vertical tangent. All right, so given the following graph G, I want you to determine at what numbers G is discontinuous and why, and at what numbers is G not differentiable and why. So go ahead and pause the video and see if you can try it on your own first. All right, let's see how we did. So discontinuity at -2 because you have a removable discontinuity. At x equals 0 because G is not defined there, an infinite discontinuity. You have a vertical asymptote. And at x equals 5, you have a jump discontinuity. So for numbers that are not differentiable, x equals -1. There is a corner right here. X equals 2. There's another corner. And x equals 4. There is a vertical tangent line right here. It's kind of hard to see. And then, of course, all the x values in part A because it's discontinuous. Remember, in order for a function to be differentiable, it has to be continuous. All right. Now, we want to determine what are the values of the derivatives and sketch the tangent lines to help you find the slope. So for this problem, you do want a straight edge, preferably a ruler, and a pencil. And this is kind of hard because it's more of estimating. So what you're going to do is, so when it says f prime of 0, that means when x is 0, you are going to go up to the function at x equals 0. So if I was going to go up to the curve at x equals 0 at this point, I want to draw a tangent line at this point. But in order for me to calculate the slope, I need to find another point. So take your ruler, draw a tangent line the best you can, so that hopefully will look something like this. And it could extend past here. That's fine. But I just did this because I was looking for a point, so I have my point in my curve, and another point on the tangent line, so I can count the slope. So if I wanted to count the slope, I would go 1, 2, 3, or sorry, this is a 0.5. So 1, 2, and 3, and then over about 1. So I would say it's approximately about -3. You do not have to be completely accurate. That is okay. It's just an estimation. All right, so now go ahead and see if you can draw the tangent lines at 1, 2, 3, 4, and 5 and count the slope. All right, let's see how we did. So at 1, x equals 1, when you draw the tangent line, you should have a horizontal tangent line. That one, everyone should have gotten a slope of 0. At x equals 2, you should have gotten approximately 3 over 2. I used this point and I went up 2. So if I was to go up 3, 1, 2, 3, and over 2, 1, 2-ish, about. All right, now at 3, you have another tangent line. You should have gotten approximately 2. At 4, you should have gotten another horizontal tangent line. So slope is 0. And then at 5, you should have got another negative line. So approximately -3/2. So if you didn't get exactly what I got with the 3/2 or the 2, that's fine, just as long as it's close. All right, now we're going to see if we can match the graph of each function in these 4 with the graph of its derivative in these four. So the way that I do this is so if I was to look at A, I first look at where the horizontal tangent lines are, because that tells me that the derivative or the slope of the tangent line is 0. That means in the graph of the derivative, at those same x values, the graph of the derivative should be when y is 0, so an x-intercept. So if I look in A, I have a horizontal tangent line here and here. That tells me that I have two horizontal tangent lines, so I should have an x-intercept right around here and another x-intercept right around here. So if I look at my options, I know 1 is out, 2 is a possibility, 4 is out, and 3 is a possibility. So I just narrowed it down to 2 and 3. Now from there, I look at the directions of my tangent line. So from the left of this tangent line, or x-intercept, my slopes of my tangent line are negative. So that means that at this x-intercept, the derivative is negative. So it should be below the x-axis. So I look at these two graphs, and at this x-intercept, the graph should be below the x-axis. And in number 2, it is. In number 3, it is not. It's above. So right there, that tells me that graph A matches the graph 2 for the derivative. All right, go ahead and pause and see if you can figure out B, C, and D. All right, let's see how we did. For B, you should have gotten 4, and the reason why, the big hint were the corners, which tells you you cannot take the derivative, so the derivative does not exist at those points. For C, you should have gotten 1, because you know that the derivative when x equals 0 is 0, so you can either pick 1 or 3. And then when you look at this, the graph right here, the tangent lines should be negative, and then they switch to positive. So that leaves you with 1. And then finally, that means graph D matches 3. So you have 3 horizontal tangent lines. 1, 2, 3. You have 3 zeros. 1, 2, 3. So just to keep in mind when you do these, always start with the horizontal tangent lines, because we know that that is where the derivative crosses the x-axis, because the tangent line has a slope of 0. Okay, now let's go ahead and look at a real-world problem and the graph. So shown is the graph of the population function, P of t, for yeast cells in a laboratory culture. Sketch the graph of, that should say P prime of t. I'm sorry, that should say the derivative. What does the graph of P tell us about the yeast population? All right, so in order for us to do the sketch of the graph, first thing is to look to see if we have any horizontal tangent lines. Not really, unfortunately. This is approaching 0. But basically, if we look at this, this right here is showing that the growth is rapidly increasing, because if you were to draw the little tangent lines, the tangent lines would be getting steeper and steeper and steeper. Then at some point, it starts to decrease. So this is telling me that the tangent lines then they're still positive, but they become less steep, and they're getting closer to 0. So gradually decreasing in growth. So that means if I wanted to sketch the graph of my derivative, all tangent lines are positive, which means P prime is positive and above the x-axis. So you know that you're not crossing the x-axis at all. So your graph should look something like this. Notice how my tangent lines start off fairly flat, then get steeper, which means that the value of the slopes start off small and get bigger. Then at some point, the tangent lines start to decrease and get closer to 0. So therefore, there's a turning point for those tangent lines. Now, what the derivative means, that should also say P prime. So the graph of P prime tells us that the yeast culture grows most rapidly after 6 hours, and then the growth rate declines. So what that means is right there at that point where you start to see the tangent line start to decrease, that is your fastest growth rate. And we can say it's about 6-ish. And if you notice on the graph of the derivative, if let's say you wanted to take the derivative of the derivative or draw a tangent line here, that is where you have a horizontal tangent line on the derivative. All right, last example. Let P of t be the percentage of Americans under the age of 18 at time t. The table gives values of this function in census years from 1950 to 2000. What is the meaning of P prime of t and what are its units? So this right here is not asking you to calculate P prime of t. It's just asking you how would you interpret the derivative of the percentage of Americans under the age of 18. Basically, you would say something along the lines that the derivative is the rate at which the percentage of Americans under the ages of 18 is changing with respect to time. That's the big thing. A derivative is that instantaneous velocity or rate. So it's the rate of whatever we're talking about with respect to our independent variable. And in this problem, our independent variable is time. And its units are percent per year. All right, now we want to construct a table of values for P prime of t. So the best way to do this is to take the year 1950, and you're going to do what we did with the car problem, is you're basically taking the average velocity. So with 1950 and 2000, the only option you really have is one side. So you would take this side, the right side of 1950, so these 2 points, and then the left side of 2000, these 2 points. Now for the rest of them, 1960, 1970, 1980, and 1990, you basically take the average rate on the left, average rate on the right, and then you average them. And that's how these numbers came about. So what does these P prime values tell you about the population? So if we look at the rate, that during the 1950s and 1960s, the number of 18-year-olds were increasing. But starting in the 1970s, the number of 18-year-olds began to decrease, hence the negative. In the 1990s, there were no change in the numbers of 18-year-olds. Oh, I'm sorry. That's the 2000. In the 1990s, because we took this rate. So between 1990 and 2000, that means there was no rate. There's no change. That's the 0. All right. I hope you enjoyed tonight, and I will see you guys tomorrow.